So, Bobby,
Oh, what are these new items?
when we are talking about
Sensitivity.
sensors, no, so you
We say some people are so sensitive. Is it something like that?
yes, I mean, I think that it could be,
Something to do with that. Yeah.
but I mean, different. When we talk about humans, we talk about emotions, right?
Yeah.
When we talk about sensors, it's more direct. It's about
Yeah. It's meant to do some
Yes,
activity. It's only
yes.
Mhm.
Maybe it's sensitive according to its sensing.
Yeah.
rather
the
than-
measure end,
rather
you
than
said.
emotions.
Yeah, correct. It is to the measure end.
To the measurement.
Is it sensitive?
Yes. How sensitive is it?
Okay.
Right.
So this is output, change in output change in output by change in input or something?
We'll see.
Okay.
We'll show you.
Okay.
We'll go through each one of them.
Okay.
So the students fully understand.
Correct.
Now, we also have this other kind of characteristics
A lot of factors.
of sensors. Now, normally, if you were to choose a sensor, what's the first few things you would look at? You talked about the temperature sensor before. You said I chose a cheap sensor,
Yeah.
and then you had some problems. Remember,
That's true.
right? So let's say I'm telling you, okay,
Get a sensor for
get a sensor. What will you look at?
maybe I will look at the accuracy.
Accuracy, yes. Yes, probably the most.
I will maybe check whether it can sense the range of interest.
Right.
Suppose it's temperature, maybe I want from room temperature to 1300 degrees Celsius.
Yes. Okay.
But if I buy something that can measure only 100 degrees Celsius, then you will send me out.
No, we no use.
What else? I may want that to work for long lifespan.
Yep. So, I mean,
I always want good sensitivity, of course, since you gave some hint about sensitivity.
right. So, I mean, here, if you look at these two, there are different tables, but you talked about sensitivity, right? Range, resolution, and accuracy, right?
Resolution, we did not discuss.
No, resolution also.
We will see later.
We will see later.
Okay.
But there are also other things like precision, repeatability, reproducibility, linearity,
Okay, correct.
drift, hysteresis. I mean, I think when you hear these words, you probably can get some idea
What it is.
what it is. Maybe.
But it's good to know formally what it is.
It's good to know with regards to sensor output, right? What these terms exactly mean. Now, you also have things like fast response, ease of calibration, selectivity. Is it sensitive to some outside electric?
Yeah, selectivity, I think is very important.
Yeah. So fast response. What about fast response? Why?
Depends on the application.
Right. So if you have some feedback,
Hmm.
would fast response be
I would prefer.
right?
Yeah.
So how quickly your sensor reacts.
Yeah. If I want the system to settle within some time frame,
Right.
I may need a sensor which has much better response.
Right.
Yeah.
Right. So your frequency
Correct.
should be high.
Correct.
Right. Ease of calibration. I mean, we'll cover this separately, but
Yeah.
let's discuss these ones. These ones are as important as the ones here. Right.
Correct.
But what I'm saying is, I think initially, if you ask anyone, they'll probably say the same thing as you: accuracy,
Yeah.
sensitivity, range. That's why I have it in two different tables, but both tables are very important.
Yes.
Right. So fast response is if you have some kind of feedback loop, right? If you want the sensor output at very high frequency because you want to change something, an actuator or something, then the sensor has to respond very fast to the measurement.
Yes.
Right. Ease of calibration.
No, I don't want to calibrate always. Because
But-
I already purchased it as to do this. It's a job.
No, but the sensors over time might change due to so many different factors: temperature, humidity.
Yeah.
I can think about a lot of different things, right?
Got it.
So in this case, ease of calibration is important because will it take minutes? Will it take hours?
Yeah.
Will it take days? Will it take months?
Whether I have to dismantle everything and then do it and so on. It depends on that.
Right. Now imagine you're the manager on a workflow.
Yeah.
Right? You have 10 sensors.
Yeah.
Now, if you have to spend, let's say, 2 weeks to calibrate the sensors, you have to probably host on your workflow, right?
Correct.
So again, how easy
Got it.
is to calibrate? Now, selectivity. What does that mean, Bobby?
Selectivity means selectivity. I'm going to select something. I want that only.
True.
So if I'm measuring temperature, my output should not change with respect to maybe humidity.
True. Now, let's say you want to measure a specific gas,
There it is.
right?
More.
Right?
Correct.
Let's say you're in an industrial environment. You want to detect ammonia.
And you made a specific sensor for that.
You made a specific sensor. You designed something, or you went out and bought hundreds of these sensors.
Yeah.
And you installed it, and everything's going great.
Yeah.
Right. Now you want to see if it works, and now you've activated the sensors. You're looking at the output.
So if ammonia is there, I will get a peak. Is it?
Yeah. So I mean, I'll make this very simple.
Sure.
Right. Let's say you have ammonia. What are these? This is oxygen, right? Yes, carbon dioxide, and let's say other gases. Okay. Other gases.
Okay.
Now, when you analyze this output,
So you are going to expose the sensor to each of this one by one. Is it?
we can. For example, let's say you're testing these sensors now, right? Same concentration. Okay. But now you can see it's
That's the output for ammonia.
ammonia.
For everything else, I would prefer 0.
Yeah, but it's also giving, something like this.
Oh, then it is not selective.
So how would you know, right?
What is the your sensor? Yeah.
Right?
It's not you. I will return it.
So ideally, you wouldn't want to be selective just for ammonia, right? And as you said, I mean, the perfect scenario would be all this is 0.
Yeah.
But in reality, you might get something like this, right? I mean, nothing is perfect,
Got it.
right? But selectivity is a very, very important factor to consider when you're choosing a sensor.
I think particularly for gas sensor, it's
Particularly for gas sensors, right? Especially if it's a poisonous gas,
yeah.
right? Okay. What else do we have here? What is the sensitivity to
Electrical and other environmental factors.
what is this? I heard this thing called electromagnetic interference.
Oh, what is that?
I don't know. When you're an electromagnetic guy, that's why I'm asking. And shielding and all these things. I mean, I don't know why.
Yeah, I can give an example. See, I was doing some measurement. I used some oscilloscope.
Okay.
Oscilloscope.
Right.
I connected, the probe. I was just hand touching it. My finger, I touched to the probe of the oscilloscope.
Okay.
I've seen that I'm generating some waveform
Really?
because the display started giving some.
Oh, just by touching.
Nice waveform.
So there's some interference there.
I don't know.
From you?
I,
By you touching? Or
of course, I'm not self-generating that.
but there you saw something.
Yeah. And then I tried to measure its frequency. Any guess? It was giving 50 hertz.
50 hertz.
Yeah.
From you. Is your heartbeat or?
Then I will not be sitting here. So that is what you meant by interference.
Yes. Some.
Because I am coupled to the wiring of 230 volt 50 hertz wiring and body. There is some capacitance. And I'm sitting on a wooden chair. I'm not electrically grounded. So there is some current flowing through. This is very, very small current.
But
I am at some potential. The oscilloscope is very good. So it is able to show that waveform.
right. And this could be a problem, right?
It could be.
If you're measuring something very small, right? If that measurement is somehow lost in that signal,
Yeah.
then you won't be able to measure it.
Correct.
Right? So we also have to check sensitivity too.
So sensors should not be sensitive. I mean, because you have sensing element, electronics, and so on.
Yes.
So if your, let's say, the electronics is exposed to such interference,
Interference.
then you get output due to that. Or
Yes. And you don't know,
yeah,
if that output is.
yeah. In this case, 50 hertz, I could make out.
Yes, 50 hertz. It's,
Other cases, we may not know.
yes.
Yeah.
So that's another thing that we need to
Yeah.
check
Yeah.
when we choose a sensor.
This is an capacitively coupled electrical interference, I would say.
Right.
Interference could be from other means also.
Sources as well, right? Yeah. If there's some sort of magnetic fields or something, then you might have to work in shielded environment.
Correct.
To cut off those.
What is shield?
Shielded, my understanding is you're kind of cutting off electromagnetic fields.
How do you cut off?
You use some material, thick, kind of, I don't even know what it is. Is it steel alloy or what?
Yeah.
Something like this?
So maybe we'll see it later.
Yes.
But
Shielding is.
what you're saying is it can be handled somehow.
Right. But this is, it can be handled, but not at the design level. This is once you have something, if you want to get rid of interference, then you could do something like that. But at the sensor level, maybe there are other things you could do to reduce that interference.
Yeah.
Right?
For example, this electronics I mentioned could be covered in a conductive
Yes.
packaging. Keep that at ground.
Yeah.
Because the example I mentioned about the oscilloscope, I was holding this oscilloscope probe and touched the measuring terminal. But it has also got another wire, which is ground.
The ground. The little
So the moment I touch that one, the signal is gone.
So that means you're grounded.
Ground.
Right. So yeah. So again, yeah.
So between the wiring and myself, if there was a conductive sheet connected to ground, then I will be safe.
Yeah. Correct.
So that's the shield you mentioned.
Right.
Got it.
Somehow cutting that interference. And low operation and maintenance cost. Now, maybe in a laboratory environment, maybe this is not
but in industry,
that's right. We are talking about sometimes thousands of sensors
yeah,
deployed everywhere, right? If you have to, replace them every 2 years.
yeah, sensor by itself is expensive. Then on top of that, maintenance cost.
Right. So these are some other things you need to consider when choosing a sensor. Okay.
Well, I think one very important thing we did not list here.
What is that?
So earlier we were saying about this sensor should not interfere with the measurement.
That is correct. Yes.
Yeah.
For example, the tooth gear, it should not touch, for example.
Yeah.
Right.
So maybe we can say loading effect or something.
Loading effect.
Or the sensor should not load the measurement.
Don't load the measure. Yes. That's important.
Although it is obvious.
It is better not to measure. Right? This defeats the purpose of having a sensor.
Yes.
Okay. Right, Bobby.
Oh.
You were talking about sensitivity before. And let's see, you have a signal output from a sensor. Okay. The y-axis, and then you have your physical input. Right? Your measurement.
Yeah.
And what do you see here? You see that the output is
actually x is the measurement.
Measurement, yes. Physical input or physical variable or whatever that is.
And so you have a linear output for certain range.
Certain range.
Yeah.
Okay. And then after some time,
it's saturated. It's unable to measure beyond that point.
Yeah. So doesn't matter, you can increase the physical input or the answer question or whatever you're trying to measure, this will remain the same. So it's safe to say from here, there's no point
correct
to measure. Right.
So its range is limited to that linear range.
Right.
Or linear region.
Right. So we talked about dynamic range before.
Mm-hmm.
Right. So in this case, I would take dynamic range as maybe to about here. Before it starts to curve and then saturate. Right? So each sensor will then have something called a dynamic range, right? Depending on output.
Or just range.
Or range.
Yeah.
Or range, yeah, right? So if you measure something beyond that, you get the same output, which means it's not really useful to us. Now, if you look at
One point is it has a range. You can, input could go beyond that, but still the sensor will not get damaged as per this diagram.
as per this diagram, yes, because if the sensor is damaged, this will go back to disappear.
Yeah. So that means there is some amount of overload it can take.
Absolutely. So is the right word tolerance? No,
Not tolerance, maybe overload capacity.
overload capacity. Because if you keep doing this, as you said, you might just let and break,
Yeah.
and that's it.
Yeah.
Right.
Yeah.
Yes.
So every sensor will have, by design, there will be some
breaking point.
factor of safety
Yes.
to until that it can withstand.
Yeah.
Although it may not measure for that full range correctly.
Yeah. Good point. Good point. Now you also said that the signal output is linear, right?
Yeah.
So, can you, using this straight line, explain what sensitivity is? What's the sensitivity of this sensor? We talked about selectivity, different thing. What is a sensitivity? How can you measure the sensitivity of the sensor, of the measurement, of this physical input?
Yeah. So suppose this is a displacement sensor. I make maybe 1 mm movement input. I may get 1 millivolt. Some other sensor I make the same 1 mm movement. I may get 10 millivolt. So the second one is more sensitive,
Give a high output.
which means the slope will be higher. The slope that you have here.
Exactly. So,
So the slope is the sensitivity.
slope is the sensitivity.
Okay.
Slope is, so it's signal output divided by physical input, right? Will give us the sensor. So you could have maybe something like this,
Yeah.
or even something like this,
Yeah.
or something like this,
Yeah.
right?
Correct.
So from here, if you go from here,
That's the lowest one.
your sensor is increasing.
Yeah.
Right. So sensitivity of a sensor is very important, as you said, because if you get a very, very small output, right? Again, let's say you use an oscilloscope, you might not be able to see it.
Yeah.
You might have to amplify it, but you might not be able to see it. But a sensor is highly sensitive, right? Will give you high output, so you'll be able to see it. Okay. Anything else from this diagram we can derive?
Info, I think good enough. Yeah.
Yeah. Okay, let's talk about resolution.
What is this random signal?
It's actually not a random signal. It looks like a random signal, right? You're right, because it's, deviating
Coming from
up and down. Yeah. Now, before we saw, sensor output and according to a physical variable. Now, let's say you're measuring something and you have an ideal output that you're supposed to get.
Okay.
Right? Say that ideal output is something like this. Okay.
With respect to time.
With respect to time.
Okay.
Right? Let's say you're only measuring one point of a physical variable, right? And the output is supposed to be like this.
Okay.
Now, let's say if you increase the physical variable, you might go like this. Okay. But now you're looking at the oscilloscope, and you see something like this. It's actually varying up and down. But overall, okay, maybe if you take the mean, you might get something like this.
If you take the average value,
you might get something like this. But in reality, it's actually moving a lot. So, at any given point, right, if you measure something, right,
it will be within some
range. I mean, it could be here. If you measure it here, it could be here if you measure it. So, what's the right value there?
Yeah.
That's a bit of a problem, isn't it?
Correct.
Now, again, let me show you two other graphs.
So this is one is 7 micrometer.
Let's say you're measuring the same. You are expecting, right, kind of a straight line, but then there's a lot of, I don't know.
So it is not due to the change in the input. Input is fixed.
Input is fixed. We are only trying to measure one thing.
You have made the sensor electronics. There is a final output coming. That is changing.
There is change. That's a problem, huh? Because then let's say, for example, you measure the next step up, right? Then you might have that next step within this.
Which I may not know.
We don't know, but could, right? Because
Yeah.
in reality, it could you should move up to a different level.
Correct.
But it's not.
Okay.
Now, let's say if you take these two graphs, for example, right? Let's say you want to measure, let's say some length or something.
Yeah.
10 micrometers.
Okay. Both of them are not.
Actually,
so-
it's true. Let's say you want to measure 20
Yeah.
or even 30. Okay. You want to measure 30 micrometers. That's the difference between one point and the other, right? Let's say you're measuring length, some length, doesn't matter what it is, right? But your first point is L1, next point is L2. You have a sensor, now you measure this length here,
So the sensor is kept at L1
L1.
and L2 location you are measuring. What's the distance?
Okay,
something.
well, let's say, yeah, it could be something like that, right? But it's, let's say, 30 micrometers.
Yeah.
Now, do you think
And your output is changing 7 micrometers.
your output is also now changes 1 micrometer, right?
Yeah.
In this case, your output is
So when I measure 30, I may get 37 or 23.
correct,
Worst case.
worst case. But you technically still should be able to measure it. Why? Because what you're trying to measure is still higher than this deviation,
Yeah.
right? 7 micrometers.
Yeah.
But can you use this one? 400 micrometers. This is going now, you can see, much higher than this, right? 400 micrometers.
Yeah. I can just keep pointing it, but no use.
Use. Because this will somehow be embedded in this, and you will not be able to really see.
I cannot resolve that.
You won't be able to resolve that, right? Because this is more than what? Nearly what? 13 times
Yeah.
higher than what you want to measure. So,
So that means this variation that you see kind of decide the smallest quantity that you can resolve. Okay.
which is called the
So when you have 7 micrometer variations there, I cannot measure 1 micrometer using this. I cannot measure 5.
In fact, you cannot even measure 7.
7.
Not even 10, because it's still
Yeah.
close to 7,
Yeah.
right?
So it has to be more than that. Or anything smaller than this 7, I cannot measure.
For sure, right? It has to be low, but maybe, you know,
Yeah. That depends on the confidence level you want for the measure.
exactly. So confidence levels, yes. So that's when we talk about the resolution of a sensor. Again, if you look at sensors, if you're trying to, choose a sensor, normally sensors have data sheets, right? And you see all the things we cover normally in a sensor data sheet.
Yeah.
Right? You'll be able to get information from a sensor data sheet. So when you talk about resolution, this is what we're talking about, right? How much it really deviates, right? And also, for example, another nice way to look at it is sometimes the sensor can be turned on, right? Let's say your sensor is turned off and you measure it through an oscilloscope, you might still see some
Output. Even when it's 0.
even when it's 0, right? So, and then if you turn it on, it might give you a certain value depending on the input. But again, if what you see before, the movement or the deviation, if that's higher than what you measure, then again, you will not be able to resolve between what you're trying to measure and that initial.
So this resolution is valid across the range.
Across the range. Right? So we talk about resolution of a sensor, that's what we're talking about.
Got it.
What is this?
Oh, many straight lines I can see. There are some dotted lines also.
I know you like straight lines and sensitivity, you can easily measure, right?
Yeah, correct.
But you mentioned something when I showed you the different characteristics of sensor we should be considering. You said something about, I will look at accuracy.
Accuracy, yeah. I said that.
What do you mean by that? I am thinking about accuracy. I care about accuracy.
It has to be, what shall we say, close to the true value.
Close to the true value. Okay. So if you look at this graph, right? You have a straight line here, right? In the middle. You can see this straight line here. This one here.
Yeah.
Okay.
Yeah. The bold or not the dotted one.
Not the yeah, exactly. But let's say that is your ideal graph, right? Now, if you're measuring something, all your points should fall on this ideal graph.
Okay. So this is the input versus output
Input
characteristic.
versus output, right? But in reality, right? Let's say you have a sensor, and you notice that your output is actually not falling exactly along this line, but it's, let's say, on either side of your ideal output. So
So some amount of variation is
there is some amount of variation, right? Now, in this graph, we can see these dotted lines show basically the range of this variation, where these values fall between.
So where is this variation coming from?
Well, this variation can come from,
Could be from the sensing element or the electronics
could be from some outside interference,
interference you mentioned.
environment.
So all these parameters
contribute.
which you don't have much control over.
Exactly. Right.
So this is kind of randomly, it may change randomly
Yes.
within that range.
Exactly. Somehow it's you can say it's out of your control, right? So because of that, it doesn't fall exactly on that ideal line we expect.
So here also, suppose if I, like the previous plot you have shown, if I am measuring at, let's say, x naught or wherever it is marked, and with respect to time, I may not be getting a constant output. I may get some dot
Varies up and down, right? But generally, maybe if you do enough tests to characterize this sensing element, for example, you might see that it falls between a certain range, right? Which is what we are.
Oh, that's what indicated by those dotted lines.
Right. So that's what we're trying to show here is that ideal output and the points might fall between two lines or range, right? And in this case, you have minus h and plus h.
Yeah.
Okay. So this is how much it changes. Now, if you look at, you talked about randomness of this, right? So if you draw like a probability distribution graph, right, then you have minus h and h, right? So that width of this, right, is then 2h, correct? So,
Correct.
So the ideal graph you can see is here, okay? But
It could vary h plus or minus h.
exactly, okay. And then if you talk about the probability, this will be 1 or 2h because everything should fall between these two dotted lines.
Yeah.
Okay, so 1 or 2h, 2h is 1, which is probability of 1. So there's a 100% chance it will fall between these two lines.
Yeah.
So that's some way to explain accuracy, right? And the range of that accuracy. And this is another way of showing it, right? You have your ideal O, right? Ideal minus h or ideal plus h, and you have 1 over 2h. Okay, so what I'm trying to say here is if you have a point, you want to look at the probability of that point falling between two lines, right? Then if you have point x, it will fall between x1 and x2. In this case, it will fall between minus h and h. Okay. So that's accuracy.
Yeah. So to my understanding, the sensor is mostly ideal on all other aspects.
Yes. Yes. Let's assume that's ideal on all other aspects.
Yeah. Right. And then you are looking at the output, but there is some randomness in the output.
Which is why we're talking about probability. Right. Yes. There is some.
So this is kind of the random error.
That
probably this is that is contributing to the resolution that you have mentioned also.
Yes.
Because there also it was random output that is coming within a range.
Correct.
So these are connected in some fashion. Or this randomness limits your resolution.
Yes. So for example, what I'm trying to say is you might do an experiment in one room.
Yeah.
right? You might see some random noise, let's say.
Yeah.
You take it to another room, it might disappear or it might be higher.
Yeah. Ideally, it should not.
Ideally, should not. But then maybe there's something like temperature or the moisture or something, some random variation in the group that contributes to what we see here. Right? So it's clear, accuracy and resolution.
Yeah.
But you're right, random. We're talking about random variation.
So the inaccuracy here is coming due to the randomness because it's in a very specific range and so on.
Yes. Yeah. The data sheet might show that it should be like this.
Yeah.
But when you measure it, you might see it falls between upper and a lower limit. Do you play darts?
I've done that some time back here.
Are you good at it?
Can manage.
I mean, this looks like a dartboard, right?
Yeah.
So, Bobby, I think one of the things that people confuse a lot is the difference between accuracy and precision. Because people say, it's a very precise instrument. What does that mean? I mean, how is that related to accuracy?
Yeah. So,
I mean, you said, so we talked about accuracy before, right?
yeah.
Do you think, looking at this picture, whoever, let's say they were throwing darts, right? I mean, this could be a sensor output and you put in different contours, for example.
Correct.
But if someone's doing that, do you think it was very accurate?
Somewhat. Not very accurate, but somewhat.
Sorry, yeah, I should also say you're aiming to be here.
Here. Okay. Yeah.
If you're aiming to be here, maybe somewhat, but
Yeah. Nearby, I would
it's
say.
nearby. Not that accurate, right?
Yeah. So the true value is at the center.
True values at the
So it's away from the
right,
true value.
right, and you can see there have been several attempts,
Yeah.
and unsuccessful attempts.
Correct.
So they're kind of all over the place.
So the error is from that center point to each point.
That's
Got it.
Right. So yeah, I'll mark that because that's a good point you make. Right. So these are the errors you're talking about, right?
Yeah.
What is it here there? Is it accurate now?
It's also similar. Its center is somewhere, but this guy is able to hit it repeatedly at some point.
Clear. So now he's somewhat improving.
Yeah.
Now he's hitting at the same point.
Yeah. But not much use.
Not use, right? Because we want it to be there.
Yeah.
So what if I tell you
Hmm.
he's not accurate, but he's precise?
Yeah. I would say he is repeat. I mean, or his repeatability is high.
His repeatability is high.
He or she, whoever. Yeah.
A person has high repeatability.
Yeah.
So when you talk about precision, or we talk about repeatability, or we talk about the distribution of, let's say, some sensor values, for example. If you take 10 sensor values, right, and if they're all
For
over
the same input.
for the same input, and if they're all over the place like this, we can safely say it's not repeatable or it's not very precise.
Yeah.
Right?
It's not precise. It's not accurate also.
It's in this case, yes.
The first figure.
First figure. Second figure, right? Somehow now the values are the same,
Yeah.
but it's still not accurate.
Correct. So it's not accurate, but precise.
This is precise.
That's the second figure.
Second figure is precise because the distribution, right, is much smaller
Yeah.
compared to the first figure.
So that way,
So now,
a dead watch
uh-huh,
is precise.
she's precise, right?
It always gives the same
Always the
reading. And 2 times in a day, it is accurate also.
So yeah, exactly, something like this maybe.
Yeah. Yeah.
So now what's happening?
Okay. So this is precise and accurate.
This is precise and accurate, right?
Got
So this is now distribution is also small,
Hmm.
also accurate. So from a sensing point of view, right? If you're measuring a sensor output, right? Let's say you're expecting 10. Let's say you're expecting 5,
Yeah.
but you're getting 10,
Yeah.
right? But everything you measure 10 and you're getting 10, something wrong. So what do you think?
That's your middle figure.
Yes, that's true. But then, from a sensing point of view, from electronics point of view, what can you do? What is it, like an offset, or is it what is it?
Is it be offset? I mean, this is for certain input or no input?
One input. Your one input,
Yeah.
right? You're expecting 5, but somehow you're getting something like this.
Yeah. So I would have said it is offset if the input is 0.
Ah, okay.
I'm not measuring anything, but already there is some output.
Right. Okay.
Because otherwise I'm not able to distinguish.
This is true.
Yeah.
Right.
Because if we are expecting certain sensitivity, if the sensitivity is more, then also I can get 10 instead of 5.
That's true. That's true. Right. So if there's no input, but it was still giving you values, then it could be a clear
It
offset,
could be an offset.
which you could probably fix.
Yeah.
Okay. Okay. So that's this. So this is the final one is accurate and precise. Okay. So that's
So we would like to have this third one.
that. Okay, Bobby. Let me test you now. You know what resolution is?
Yeah.
Okay. You know what accuracy is? Okay. Now let's start with this graph here. Right? Here you have your perfect ideal sensor. Okay?
Yeah.
And to the left here, you can see in red
I can see a staircase also.
and also a staircase. Okay. That's
What is that red one?
red one is just a line joining this staircase.
Okay.
Right? But let's say your sensor output is the staircase. Do you, in terms of accuracy and resolution, how can you explain this first graph?
I need to compare it
Yes, okay. Compared to, yes, you're right.
compared to the
Correct. No,
continuous line.
let's compare. You compare to the straight line.
Yeah, compared to the straight line, of course, the resolution is reduced.
Resolution is reduced. Okay.
Because for I'm let's say changing input, for some time there is no output, then there is a change in the output.
Right.
So that means some smaller changes it's unable to detect,
Correct.
or I am unable to resolve smaller quantities.
Right.
So staircase output I have,
Yes.
but I also see some deviation from, the slope itself is changed.
So what can you say?
So there is a error in the
Error.
gain,
Yes.
or error in the slope.
Yes. So you could also say it's not very accurate,
Yeah,
right?
yeah.
Low accuracy.
Or that error in the slope will introduce an error. Or will affect the accuracy.
Okay. What about this one? Let's make this A and B. A, B.
Yeah, between A and B, maybe I will prefer B because at least it's there is no gain error, or slope is the same.
So here you said, okay, so here, if you compare these two,
Yeah,
right, this one has better
limited
accuracy,
resolution,
limited resolution.
but higher accuracy compared to A.
And also high accuracy. I mean, if you compare the perfect ideal sensor, it's
Close to that. Yeah.
high accuracy. Now, look at C.
See, you keep it. I don't.
Why? This is a nice staircase, right?
I need to climb. It's so big. Resolution is so bad.
So here, especially if you compare now, if you compare this one to this one, we can clearly see this resolution
It's much worse. Yeah. Correct.
right? But it doesn't stop there. It gets
It has additionally the gain error also.
it has some error. So bad resolution and bad error. Right? Low,
We cannot say.
it's not accurate.
Yeah.
Right. What about this one?
T is poor resolution.
Still poor resolution, right?
Yeah.
Because of these
Correct.
large steps.
Correct.
But at least it's accurate.
Yeah, I can also solve smaller quantities.
So out of if you were given a choice, you would
I'll go with D.
you go with D. Right?
Yeah.
Okay.
I passed or
You passed. I thought you even got angry when I showed you C. Bobby, now I know you like straight lines,
yeah, of course.
right?
Yeah.
And we've been talking about straight lines all this time.
Correct.
Right? And I saw when the sensor saturated, you said, forget about that part.
Yeah.
Then we cut it and we had a range.
Correct.
And you found the sensitivity. You were happy.
Yeah.
But now here's a problem. Right? Here you have an ideal case.
Yeah.
Right? Ideal sensor is straight line,
Yeah.
which is what you like.
Correct.
But you go to the lab and you're now testing a signal output. It's something like this.
Yeah. It's, I don't know how to explain. Is it slipping in between or what? I mean,
It's not straight.
yeah.
Right? I mean, if you had this ideal, you'll have something like this, no?
Yeah.
Yeah, A plus A, you have your
It's a straight line.
straight line. K is your gradient, A is your intercept, right? You have a nice output, but in reality, you are getting something like this. Right? And which means what? There is some nonlinearity.
It deviated from the straight line.
Deviated from the straight line. And there's a point where there is also a
Maximum.
deviation. Right? So sometimes sensors do this.
Mhm.
They deviate from that line. Right? And obviously here you can calculate the maximum deviation. And then that is related to the maximum nonlinearity. Right? As percentage of the full scale.
Okay. So this O max and O min are
This is the maximum here.
okay.
Right? And this is the min.
Okay. So the maximum output by difference between maximum output or
Yeah.
difference of maximum output to minimum output.
Yeah. Obviously, this is the range you're trying to measure.
So that's the range.
Right? And
N cap.
N cap.
Yeah. N cap is the
This one, yeah. This is the maximum
deviation.
deviation. It will give you,
Ideally, it should be 0.
ideally it should be 0, yes. But because of this, you'll have to add that term now.
So this introduces some, what shall we say? I mean, as input changes linearly, output supposed to change linearly.
Yes.
Now output we have some harmonic content probably.
Yes.
Because it's a non-linear characteristic.
Correct. So does this depend on the sensor or the back end of the measurement system, or does it depend on outside interferences? What could cause something like this?
Yeah. I would say not much on outside interference. Probably mostly to do with the sensor itself and its electronics.
So if you buy a sensor that shows a linear output and later on, can it become non-linear?
I think we cannot generalize.
Right.
Yeah. Right. Because I think the manufacturer usually test it for its lifetime. And if the company says, okay, non-linearity is 1%,
Yes.
for 10 years, I think they have passed that test.
Some
So we
sort of
can
a guarantee saying that it's
guarantee that.
right. Okay.
Because they do some accelerated aging and then test.
So generally, if a sensor is linear, it is supposed to be linear. Generally.
Yeah.
Right. Okay. But we do also see this non-linearity
Correct.
consensus. Right. So, but then we have to act accordingly and then consider that in the equation.
Yes.
In which way? Right. So that's linearity. Bobby, I'm back to this, your favorite device.
Yeah.
You remember this device, right?
Yes.
Surely.
The spring.
The spring.
Yeah.
That's
I was thinking the spring, that can also, now since you mentioned
non-linearity.
non-linearity, the spring could be a source.
Right. Where could
But the spring constant we say K, but as you press, it may change a bit.
That's true.
Yeah.
And as you release, somehow also. Right?
Yeah.
So it's going up and down.
Correct.
So you have a problem with that. Then.
Yeah. So one good, example for, reason for the non-linearity could be this.
So if you have a spring system in a measurement system, that could cause some non-linearity. What if I tell you?
Is there a way to...
What if I show you this?
What is this? You are using weights?
The spring that you don't like
Or you have removed it?
has disappeared now.
Nice.
But then you also said before, wouldn't this just go up if there's no spring?
Yeah, it will just go and hit.
We just go and hit.
Yeah. You cannot use it for measurement, so you need to have that spring.
So how do you avoid that?
Oh, so now you have made that plunger to go out, and then you have kept a weight.
You saw the weights, huh?
I saw the weights.
Now I have some weights there.
Also, there is something called datum level. What is that?
Yeah, your scale. I know that you also did not like this scale and the pivot. So I removed everything that you did not like.
Okay.
Right?
So you are a so friend of me. Thank you.
I had listened to you, right? So when someone says your sense is not good, you have to improve it somehow. Correct. So now I have a datum level here, and I put some weights here.
Oh. So that means if pressure increased.
It's still just close.
Yeah. Pressure increased. What am I supposed to do?
If the pressure increases,
it will go up.
We have to somehow simulate what the spring does. Then you have to put something on top of it.
Oh, so I keep changing the weight until it comes back to some.
You have to keep changing the weight.
Comes back to this
datum level.
Okay.
And by doing that, you can get rid of the spring and
non-linearity.
And hopefully can get rid of the non-linearity.
A smart idea.
But then someone has to keep putting the weights.
Yeah.
That's the only
It could be done using some automated.
Yeah, that's true. You can somehow have some feedback loop and just drop the weight or something.
Yeah, that way, or somehow generate magnetic force and push down that one. Many things can be done.
That's actually a smart idea.
But in that process, I mean, you have removed the spring and things like that.
Yes.
So
and the scale also, right? Yeah. You don't need a scale anymore. Because the more things you add to a system, right, the more errors also you're introducing more errors as well, right?
Correct.
Now this pointer that you see here, right?
Yeah.
If there's some dirt or something, it might not move perfectly.
Yeah.
Right? But in this case, we've got rid of that.
Correct. So that way, I mean, this I'm able to relate it to something else. I'm thinking what it is.
This? Yeah. A second more?
Yeah. See, you are always bringing back to a null point.
Yes.
A point where you started.
Something like a
balance
system?
Yeah. Or, correct. So it's a balancing type measurement.
Right. Right.
Where you are actually not using any pointer and things like that.
No. I mean, the more moving parts you have,
yes,
the higher there, I think, possible to probability of error. But in this case, the only limitation is probably you have to keep adding weights. But then, as you said,
it could be automated.
It could be automated
using some other. So this you are using as a mechanism to convey that non-idealities could be, removed using, if you make some changes in the way that you measure.
Yes. So in this case, again, initially maybe this system, right? Maybe this is not a system that you can buy from a manufacturer. Maybe use some homemade system.
No.
It could have been linear in the beginning, but after some time,
correct,
there could have been some rust on the spring or something.
Yeah.
That could have affected.
So that aging factor is also removed.
Aging factor is also removed.
Oh, cool.
Right. So there are, I think, ways to remove non-linearity. Sense.
So if there is a possibility, it is measured. I mean, good to measure in this balancing method.
Yes.
You make a balance between input and output, make them equal. You are only meeting that requirement.
Correct.
In that process, you have removed other errors.
Yep.
I mean, other sources of errors.
As a source of errors.
Maybe we will see something like this later.
Later on, yes. Correct. Okay. What do you see here, Bobby?
Or you have moved this straight line. Huh?
So, no, let's say we have a scale reading.
Yeah.
And we are measuring pressure.
Correct.
Previous example.
Yeah.
Right? So, this is your nominal characteristic.
Yeah.
But, somehow,
Hmm.
this is what you're supposed to get.
Correct.
Somehow it's moved. Let's say this is 0.
Yeah.
It's drifted.
Yeah. So you have an output even when input is 0.
No, yes, exactly. I mean, ideally it should be 0.
Correct.
But what we are saying is we have some output.
So this is what you meant offset earlier.
Yes. So it's basically it's drifted from
Its
original point or where it's supposed to be.
Mm-hmm.
Example, right? What about here? Here we have a 0.
So you
right?
have maintained, I mean, there is no offset in this, in the second one.
Yes. So here we have a 0 drift.
Yeah.
Okay.
Throughout. So its slope is same.
Yes. But here
the slope has changed.
Yes. But so here we don't have a 0 drift. We have a sensitivity drift.
Correct.
Right? Sensitivity has somehow changed. Right. So here we have a 0 drift. And here we have a sensitivity drift.
Yeah. Or a change in sensitivity.
A change in sensitivity, yes. Or changes.
Yeah.
Change.
Because it's not keep drifting.
Yeah. It doesn't go like this.
Yeah.
Right. Yeah. So let's say sensitivity change.
So these are actually, this looks like very systematic error, not the random error you mentioned.
Because random error cannot be this nice. Right?
Correct. It will be keep varying.
It will keep varying.
Yeah.
Right. What about here?
Or it's a combination of both.
You have 0 drift, right? Plus change in sensitivity.
Okay. Yeah. So either 0 drift or offset error, that's also acceptable.
Yes,
term, no?
yes, offset error, yes.
So sometimes for the sensitivity change, people also say gain error.
Gain error for the change in sensitivity.
Yeah, for the second figure, for example, it's a, I mean, if I consider it as a slope, agreed, but easy to convey also a gain. We are expecting a gain of so and so, but it has changed. So it's a gain error and offset error, or 0 drift and sensitivity change. So these are systematic.
These are systematic errors because otherwise, as you said, you will not get a straight line.
Yeah. So when it is systematic, we may be able to systematically remove also.
Exactly. That's the advantage of such offsets or such gain errors. We might look at it and go, okay, we can somehow build up to it.
Yeah. Because I can make a measurement at no input, I'll get the offset, I can subtract that.
Yes.
Offset error is gone. Yes. Gain, I may have to measure at 2 points and see what's the slope. The slope is different. We can do a correction for that.
Exactly.
But this cannot be done for the random error.
No. Like what we showed before with resolution, for example.
Yes.
Right? It's moving up and down.
Yes.
No. Because if you test it 10 times, you could get 10 different answers.
Yes.
Right? So normally with offset, generally it's the same, right? You would probably see the offset is the same if you test it multiple times. So this is example of a 0 drift, offset error, as you said, or a sensitivity change of the sensor. Also called gain error. So, Bobby, let's get back to this. We talked about resolution before. What do you see here? Let's say, I mean, this is just to show several of the concepts we talked about in one picture. Okay, so the students actually understand, right? So here, let's say you have a sensor output, right? And you expect the sensor output to be along this line.
Okay. This is with respect to time.
With time, let's say.
Yeah.
Now, when the sensor is off, okay, when there's no input measurement, it's still giving you something like this.
That is coming from that randomness.
Quite. But ideally, it should be a straight line.
It should ride on that straight line.
Right? Yes, exactly.
But it is riding somewhere else.
Very good point. Right on the straight line.
Yeah.
Now, when you turn the sensor on, when you expose it to the measurement or the
Yeah.
physical quantity,
So there's a change due to that.
right? Which is you see here, right? The signal change.
Yeah.
But do you see even in the signal change, there is some
Noise
noise here
or randomness.
or randomness.
Both are same.
Yes. Now you take the measurement away from the sensor, it goes back. It should go back to 0, but again there's some randomness.
That story is continuing.
Yes. But
Okay.
two things. You see this thing deviating noise,
Yeah.
which is a random noise.
No.
But it's not only that. You can see there's also a drift. So this is supposed to be on a straight line, something like this.
Yeah.
But there's a drift here.
Yeah. So it could be due to maybe sensor electronics got warmed up, or the temperature has increased,
For example.
and maybe the gain is slowly changing,
Yes.
which is provided by the electronics. Could be something like that.
But as you said, if this remains the same, right, then we will be able to somehow correct it.
If you can measure that slope.
If you can measure that slope, right? If you keep measuring and if you see this is going up like this, right, and if it stays along this, then you can measure this strip.
Because to do that, you may have to give non-input.
Meaning?
If I want to measure the slope,
Yes.
I need to give an x1, x2, y1, y2.
Yes.
So I need to know what is x1 and x2. If my sensor itself is behaving like this,
Yes.
I may have a problem.
Yes, that is correct. Yes.
So it may be possible in certain applications.
Yes. But not all of them.
Not always.
Correct. Correct. Now, one of the things that we measure,
What is this S and R?
right, so we know what the noise is. So do you think if you have a graph and output like this, you should be able to measure the noise level, right? Because it seems like it's
Noise I can measure.
noise, right? It seems like it's falling
Correct. It's like your plus or minus 2,
edge, right? It's falling between these upper and lower limits, right? So if you can measure the output noise, and you know what the output signal is, when it's exposed to a measurement, it gives a certain signal,
Correct.
right?
Yeah.
Then you'll be able to measure something called a signal to noise ratio.
Oh. So how good is my signal with respect to
Noise. So that means if two examples, right? One, you could have something like this noise, okay, and then if you expose the sensor to the measurement, you might get something like this, and then you turn it up again. In this case,
even in that portion there will be the same noise.
yes, but there's only a small increase in the sensor signal. Here you can see this; it's quite high compared to the sensor signal. So, if you're looking at the signal to noise ratio, normally it's measured in decibels. Okay, it's a ratio. You take the logarithm. In this case, your signal to noise ratio will be higher than
What you're drawn.
what have drawn.
Yeah.
Right.
What is good? In the sense, ideal case
Ideal case, we want a good.
is no noise.
Ideal case is no noise. Ideal case is something like this.
N0 will be 0.
Yes, I remember something like this.
Yeah. So in the SNR, S0 by N0, N0 will be 0.
0. So
But all practical cases, there will be some N0.
yes, it has to be at here. Yes.
So if I want to improvise this, I need to work how to get more output voltage and also try to reduce the N0.
Yes. Yes. Because you could have a small noise, but your sensor output could also be very small. In that case,
Correct.
right? But then, if I connect this to, let's say, if I connect this, for example, to an amplifier, right?
Yeah.
What's going to happen? Am I going to increase the noise and the signal, or can I make it in a way I could only increase this one?
So you mean will the SNR be better after amplifying?
Yes.
I think it will be the same because you are amplifying both.
Yeah, amplify the noise as well.
Unless otherwise I can selectively amplify the signal of interest alone. I cannot improve the SNR.
Right. So before we talked about amplifiers of sensors, so if you have noise, you are amplifying the noise as well.
Yeah.
So your SNR probably wouldn't change so much.
So in some cases, we may be able to use some filters to suppress the quantum noise a bit.
Before sending it to the amplifier.
Yes. In that case, it can help.
And also maybe after.
Yeah.
And do some.
Any place. Yeah.
You know.
Probably before.
Right. But if you have an amplifier, it amplifies both.
Yes.
Generally.
Yes.
Okay. Now, we talked about noise a lot, right? And you said random noise.
Yeah.
And, I gave some examples. You gave some examples. Temperature, moisture, and all these things.
Yes.
But it's more serious than you think. Noise is a problem when it comes to sensor output.
Yeah.
So, in fact, you can see here there are different types of sensor noises. Right? You have your intrinsic noise. Now, this could come from the sensor itself. Right? If the sensor has movable elements, mechanical elements, that could introduce some error.
Yeah.
Okay?
It could be electronic also.
It could be
In the sense, if it's a resistive element,
of course.
that element itself will generate some noise.
Of course. Interface electronics, straight capacitors,
Correct.
things like that. What else? Just Johnson noise.
Yeah, so all this come from
Different types of noises.
Yeah.
Right?
Yeah.
Yeah.
So in general, noise can come from the sensing element. Also, it can come from the electronics that you have.
Right. So you're saying that means it could come from the whole measurement system.
Yes. And yesterday you were mentioning an ADC, analog to digital converter.
Yes.
That guy will also introduce some noise. I think.
So we should not use that.
But if you want to digitize, probably there is.
We have to use stretch. Correct. Right. So these are called intrinsic noises. That's to do with the measurement system. We also have extrinsic noises, right? That's what we've been talking about.
That is something like this interference.
Yes.
Yes.
Or it could be random noises too, right?
Yeah, it could be random, but it is from outside.
Yes,
is it?
Like, yes, like EMI, electromagnetic interference, crosstalk, substrate noise, and all these different kind of things. So we have to deal with a lot of sources of noise.
Yeah. So these are the things that we need to know in detail if you want to design a sensor as a complete system by ourselves.
Correct. Got it. All these different things we need to consider. Now we talked about straight line graphs. We talked about nonlinear graphs. What is this?
Yeah. This one is going up in some way, coming back in some other way.
Very good point.
And so on.
Very good point, right? That is exactly what it's doing, right? So you're starting from, let's say, somewhere. It's going up, right? And you think when you decrease this measured variable, it should come down the same way, right?
Yeah, no, doesn't follow.
That's what we've seen before. But it's following a completely different path.
Yeah.
Then it goes down.
Yeah. And comes back
a different way.
Yeah.
What's going on?
So that's the characteristic of this guy.
This guy.
Yeah.
So
if it's a sensor like this, it's not very useful.
Yes.
I mean, whether I go from 0 to this side or I'm coming from full range to some other point, I should get the same reading for the same X.
Right.
This same X, there is a possibility to get two readings.
Right. But you can also see, though, it's somehow similar going up and
That is
down.
true.
Right? In one cycle.
Yeah.
Right? But what if we can measure this output hysteresis? So here, obviously, it's how much. So it's supposed to be here, but it's here.
Yeah.
Right? And here, in this case, it's supposed to be here, but it's here. Right? So you can measure the maximum input. It's called hysteresis, when it doesn't follow the same path back. And you have also a maximum output hysteresis. Now, what examples can you think of? I mean, for me, I have seen this with magnetics.
Yeah, I also have seen.
Right?
Yeah.
These magnetic materials, right? When you magnetize them, right? It goes up. And then if you kind of reduce the applied magnetic field, it doesn't come back the same way.
Yeah. It just got some residual magnetism.
Right? For us, case in the spring, is that a possibility? It goes up one way, then comes down slower or a different way?
Spring may have I mean, depends on the material properties.
Uh-huh.
Yeah. But if sensor has got this kind of characteristic,
Uh-huh.
I will hate that sensor.
But then I think maybe, I mean, from the top of my head, there are some magnetic sensors that has windings
Correct.
and cores. So I think we might come across sensors like this.
Yeah, I will be fine if the width is very, very small.
I mean,
Yeah. So this.
input histories.
Yes.
This one.
Yes.
Make it something like this.
Yeah. So if it's very thin,
Thin. Then you wouldn't mind.
then I will not mind. Then it has become like your plus or minus H or something. I mean, for the same input, I get two readings, but they are nearby.
But do you think something like this can be somehow exploited, somehow utilized to make a sensor? Because now we are only thinking about input, output, right? But maybe, I mean, I think later on we'll talk about a specific magnetic sensor that utilizes this property.
Yeah. If you want to memorize maybe something, it remembers, I mean, okay, I went there and I am coming back. So,
yeah. But idea you would not want something.
yeah, a sensor, we would prefer not to have this hysteresis, but hysteresis may not be avoidable in certain cases. But we would like to keep that fit as small as possible.
Small as possible.